Okay, so hello and welcome to my online ACCU talk. This is going to be interesting, a new challenge for me. I did online talk last year, but it was all live code and it was a joint one, so I didn't have to deal with any of these exciting things like pop-up Q&A things and things. So I'll try and kind of like manage things as best I can. I've got a brilliant track host who will hopefully prompt me if anything goes a bit wrong. Hope you can all hear me. Do get in touch and I'll get notified if something does go wrong technically. I had great fun this morning. About half an hour before the presentation, the power, which the local power is usually very reliable. I've been working from home for a long while now, and it's almost never been an issue. But it went out for 5 minutes, which caused me interesting new set of anxieties. So I actually have sufficient UPS power to ride out those short couple of minute outages, but if it goes down for too long, eventually my computer will shut down and I shall disappear. So hoping that doesn't happen. So if I, yes, I do have control over my slides. That's good. So welcome. My name's CB. I work at Bloomberg, and this is a talk about things that I learned while trying to avoid becoming a CMake expert, which is a bit of a long talk title. And I've also discovered that when you have a long title, often it's good if you can kind of like abbreviate it and make it succinct. And a lot of the time you kind of like end up removing words from the end of the title. But I discovered that this one actually abbreviates quite well from the beginning of the title. So yes, my advice is to avoid becoming a CMake expert. So one of the roles of my job is to make the use of our library and framework as easy as possible. And as a result of that, I inherited kind of maintainership, if you like, of a couple of CMake modules. And I didn't kind of write them from scratch. And I moved into a project, having not used CMake before, where we used CMake as our build tool. So I've kind of like been learning as I go along, and I've come across a lot of fun stuff that you can do with CMake and quite a few of the surprises. So this is kind of like just an introduction to what I've kind of discovered along the way. So what is CMake and why might you want to use it? CMake is a build tool or a build system generator. It will generate a build system for a project, which is then run by a build tool. So this is kind of like a new way of doing things for me, but actually in some ways it does fit in with the way a lot of tools have worked in the past. So if you look at how to operate CMake, it kind of fits into the same slot as a traditional configure script in some ways. And in fact, CMake has kind of like given itself an interface where you can like use it like that, and it almost appears like that. So you can make a build directory and do CMake ... which is a bit like /configure if your build directory is just in your source folder, and then you can run make, and then you can run make install. And so CMake kind of like can trick you into sort of thinking it sits in that slot. But it is, and it also kind of does a lot of the similar roles. So configure and the auto tools around your traditional Unix configure script have a lot of capabilities for detecting features of your system and setting them up. And actually, if you dig into auto tools, there's an awful lot of knowledge embedded in them. A lot of that knowledge is around systems that people hardly ever use anymore and are possibly only kept alive in museums. So is possibly of questionable value in a modern tool. And CMake does sort of similar roles, but probably supports fewer platforms in theory than many configure scripts, but probably supports about the same number of platforms in practice, because platforms that are never used are going to configure rot quite easily. So another kind of like way I kind of think about it is CMake is almost like a higher level language for describing your project and how to build it, and then the actual tool for building it is more like an assembler. It's not a perfect analogy because the build tool is actually kind of like running things, not creating something for a run. But it kind of like, yeah, it works in a way. CMake is like your C, and your build tool, which might be Make, is a bit more kind of like low level, like an assembler. So generally there are two popular Make systems that CMake can use, and it can also generate a lot of other things. So CMake by default, if you're on a Linux or other Unix system, will generate make files, which can then be run typically by GNU Make. Other makes are available. I haven't ever tried them with CMake, but that's probably quite niche. But CMake will also have some capability to generate things like Visual Studio project files, if you wanted to. I will confess I haven't. I've kind of tried that once, but I didn't actually kind of get further than just kind of running it and going, oh yeah, it did something, because I didn't actually have Visual Studio around when I asked it to do that. Probably the most so these the things that it can generate are called generators. Unix makes files is its default, but the one that I typically use is Ninja. So Ninja is a kind of high performance build tool, but it's designed to be a low level build tool. If you're writing a Ninja file, you tend to kind of end up writing things longhand with like a lot of repetition, but what it does do really well is it parses Ninja parses its input very fast and is very quick to scan dependencies and do incremental builds really well. So if you look at the performance of GNU Make, it tends to be not great on larger projects, and so if you run Make with some of the debug tools, it's amazing how many intrinsic rules it scans of things that it might want to do in case there's something available. So Make will scan for RCS version control files to see if like it can create Make files out of Makefiles, Vs, which almost nobody uses. So you can kind of like discourage Make from doing all of those inbuilt things, but it's work. And Ninja just tends to be faster, certainly in the use cases that I've experienced. So CMake is supposed to give you a high-level way of describing how to build your project. It is very popular now. I don't know if it's quite reached kind of Git levels of popularity. So the way I kind of like you look at Git is it's like it's pretty much won the version control wars at the moment, even though other version control tools are available and sometimes have better features and some people say better UIs. CMake is definitely kind of winning in the space of building C and C++ projects. Try to click. I can only hit space to advance slides. As I said, I've maintained a couple of CMake modules, which is a way of extending CMake with new capabilities. So why might you want to do this? So CMake, as it stands out of the box, is very capable of building your typical C++ project, which may consist of multiple libraries, multiple executables, and generating build files. So it can be built by a kind of parallel build tool. But there are always kind of special cases in various projects and teams that you might want to address. So a couple of examples that I've kind of come across. So compiling application data. You may have in your application some data that's in a source format. So maybe it's described in an authourable text kind of based format, maybe structured text, and maybe your application uses this in some sort of, maybe it's got some sort of read-only database that it starts up, and so it can kind of operate on these structures. And maybe you've got this a tool that can compile the input into the output, and then you want to embed that output in your tasks so that it's fast and readily available. Yeah, you could use CMake to generate rules to compile your application data, and either embed it in the executable or into a faster binary format that your application uses. Code generation. So this is the one that I was sucked in to help maintain. You may have some sort of input, and you may generate specialized classes from it. I know that die-hard C++ enthusiasts will always prefer to extend the language to make it simple to express exactly what you want in C++. So I'm kind of quite excited by some of the new proposed features coming up, which makes making classes of a particular flavor really easy and intuitive. But as it stands at the moment, a lot of people kind of like do generate code of a certain form, may contain certain boilerplates from some other input. So I know at my company, we have kind of XML schemas from which we generate a sort of standard format of class that provides value semantics, and we also kind of have things which supply encoders for those classes for specialized serialization, deserialization. So one of the modules I maintain does a form of code generation. And the other thing is kind of simplifying project-specific boilerplate. Maybe you kind of like add certain kind of inbuilt functionality to all of your libraries, maybe stamp a version into it or something, or maybe you kind of like do some installation of config files alongside libraries in a standard way, and you just want to kind of like codify that in a simple way. These are all kind of like things that you might want to do in your build system that you could extend CMake to help you with. Just keeping an eye on the time, because I'm another thing that I remembered is that I've done an online talk before, but not one with slides. And for better or worse, I do not have a dual monitor set up on here. So I'm full screen in order that the slides look their best. But that means I don't have a clock on the screen. So I'm just kind of trying to, I've popped a clock next to my camera, but it's an incredibly dim clock in brightness. And so I'm just struggling slightly to read that, make sure I'm keeping on schedule. Looking good so far. Yep, haven't seen any questions come in, so I assume everything is totally clear. I'm kind of happy to interrupt myself and answer anything as it arises. So getting started with CMake. So CMake, when you run it, is a build system generator. So when you look at the input files, there are two kind of main phases. Okay, this is a simplification. CMake can do lots of things. CMake has functionalities for finding dependencies and pulling them down. It has functionality for installing things into an install directory. It has facilities for running suites of tests that you build. I'm going to talk mainly about just the core part of CMake, which is generating a build system and running it, for which there are two main steps. So when you're authoring a part of the CMake system, there's two main phases. There's the configuration step, which is essentially where CMake parses your CMake lists files and generates a build system. And then there's the build step, where that build system is executed. And you can use the native build tool for which CMake has generated the build structure, or you can use the CMake command itself as a driver to run the build. And sometimes when you're authoring stuff, it can be easy to kind of muddle what's happening at the configure step and what you're describing affects the build step. So sometimes it's good to kind of just take a step back and work out what you're changing is influencing. So I think I've probably talked my way through the next 2 slides. So yes, so during configuration, CMake just kind of like you give CMake a source folder. It opens the CMake lists at the top level of that source folder, interprets what's in there, and based on what it's found, writes out a build tree in the build directory. And it's very much a sequential process. It's just interpreting the commands in sequence, and it just looks at the top level CMake lists up until the point that you add other subdirectories or include other CMake modules, where it will include those again in a sequential manner. So it's kind of a fairly simple top-down process. And once it's kind of like read all of the CMake lists and anything you've included and any subdirectories you've told it to go into, it'll write out all of the build commands for the project, and then it'll be ready for you to execute a build. And then the build tool is an external to CMake, something else. And typically these are kind of like support high concurrency. So if you've got multiple threads or multiple processors available, multiple cores, you can build lots of things at the same time. And typically also they will support incremental build. So if you touch a source file, just the object files that are generated by that source file have to be rebuilt, and then only the things that link that source file in need to be relinked. Whereas, and this is kind of like in stark contrast to the configure step, which is very much sequential. So if you're doing some customization where you call out to an external command, CMake will run that external command, wait for it to finish, and then carry on. So no parallelism, almost no parallelism in the configure step. So I've just seen a question come in. Is there a good way to use code generation with CMake in a way that integrates well with an IDE, no squiggly red lines when using the generated code? It depends on how you do it. So I'll probably come to this story at the end, but we have sort of solved this, not in the most beautiful way, but in an interesting way that does work. So typically the recommendation for code generation is that you set up the build rules so that code is generated at build time rather than configure time, which gives you parallel generation, incremental generation, and it sets up the dependencies so that targets using an object file that use a source file that is generated know how to generate that input source file and then kind of link that into your application. The disadvantage is that after the configure step, the generated files don't yet exist, and they don't get added to, say, a Visual Studio project or other IDE things at that time. They only kind of like come into existence in a build directory, and the IDE doesn't necessarily know about it. So the alternative is to generate them at configure time by using some process that executes the generation step at configure time, and then deliberately adding the generated files to the project with something like a target sources command. And that will add things into the generated project. And also you can set up kind of include paths for the things so that the IDE should be able to find them, and it should work fine. And like there's a big tension there with like one approach, you've got kind of parallelizable incremental code generation, which is all good. And then if you switch it to, but you don't get the files added to your project. Whereas if you do it at configure time, unless you do something clever, you're left with like sequential generation, which tends to be a lot slower, and often you don't have incremental generation. And I'm going to get back to that point later, because there are ways around it. But yes, there isn't an easy, perfect way. And a perfect way should not be difficult. Okay, so what does the CMake List file look like? This is probably about the simplest thing that actually does anything is. So you can actually leave out the top 2 lines and start with a one-liner, but CMake will moan at you for not telling it things that it wants to know, such as what version of CMake did you run against, and what languages are you using, and what would you like to name your project. So the top line, CMake minimum required, specifies what version of CMake you require. 3.19 is a while old, at least a year. It just happens to have some features that I've been kind of coding against and required. CMake 3.23 is out fairly recently. By setting the version, you will ensure that you get a diagnostic if an older version of CMake, which may not be compatible with what you've written, is used to try and build your project. There is actually a clever syntax you can use to say, hey, I need only version 3.1, but I'm good with the policy. Should I go into policies now? I'm looking at the time. I think maybe I won't. So you can specify a range of versions that is the minimum that you required and the maximum that you've tested with. So that can sometimes be useful. Project gives a name to your project. That, as far as I can tell, doesn't have a lot of effect on the build. It sets a CMake variable that you can then kind of like use to write out files if you want. But the project name is not particularly important to the build itself. And then you've got a languages declaration in the project, which says what languages am I using in this project, which tells CMake when it's kind of searching for compilers, which varieties of compilers you need. So yes, you can use C and Fortran. I don't have a full list of languages that CMake support. I tend to just use it with C++. And then finally, the final line, add executable, is the simplest specification of a target. So in this case, we're building a program called hello, and it's got just one source file. It's main.cpp. So it will try and compile hello from main, and that's it. That's it. So I think. Yes, so it's demo time. So I've got this set up. I just think it's kind of like reasonably instructive just to see kind of how this works. I had a quick play in VS Code, and I thought maybe I could show this in VS Code because that works, because VS Code's got some CMake plugins. But I ended up kind of explaining my way around what VS Code was doing in the background, and I thought that possibly wasn't as useful. So I have here, I think. Oh, I didn't clear the screen. Never mind. I have here a demo screen, so I shall go into my freshly prepared folder. No, I won't, because I'm there. So hopefully somebody will ask a question or otherwise notify me if this is invisible or not yet shared as I intend. But you should see my solarized dark colored terminal. And to prove that I am about to do what I say I am, this is exactly the same CMake lists as I showed on my slide. Just check that notification. I'm just kind of keeping up with my track host there. Yep, good. Everything apparently is good and readable. And then if I look at my main.cpp, it's a very simple hello world, and it's C++03 compatible because I'm very old school and familiar with C++03. Cool. So there's almost nothing else in my directory. I'm going to kind of ls-a. So this is a Git repository, and it has a git ignore, but there's nothing else in here. So there are a number of ways which you can invoke CMake. and you can make a build directory, change directory into the build directory and run CMake from where you want to build, pointing it at the source directory with just a single parameter. I tend to use the two option version where you specify a source folder and a build folder. I just find that I don't want to kind of manually create a build directory or change into the build directory to run CMake. So I'm just going to do that now. So CMake -S, it gives you the source folder, which is this folder. B supplies a build folder. So I'm just going to call it build, which is that's what VS Code was using, tends to be the simplest. If you're going to have multiple build folders, you might want to name them after the configuration parameter. And then the only thing that I'm going to explicitly specify to override at this stage is I'm going to use the Ninja build generator. So I'm going to get Ninja files. I'm just going to run that now. So you can see the kind of output here. It's quite kind of classic CMake output. Informational messages prefixed with like a double dash. So that should give you a warm, fuzzy feeling. Things that aren't prefixed by a double dash sometimes are coming out on standard error and standard out. If you're kind of like running it in the background, tend to be more important things like warning and errors. If you've got like a colored terminal, these days warnings can come out in yellow and errors can come out in red. Obviously, you can kind of configure that as well. But if it runs successfully, it generates a build tree. So if I now look in my folder, there is now a build directory. And if I look in the build directory, there's a build.ninja, which is what Ninja uses to build. And then also a kind of like a couple of, there's some sort of CMake internal. So you can see there's a CMake cache, which I'll come on to later, and CMake files, which contains various internal things internal to CMake. But you don't tend to need to explore into the build directory too often, I find. We generated a build system. We haven't kind of created anything. Should we try running the build? Yes, why not? So you can run the build just by running, in this case, the Ninja tool, or you can run CMake with the build option, which is just a kind of like simple way to invoke it. Also means you don't have to kind of remember which generator you did it. If I generated it with Unix make files, the build command from CMake would be exactly the same. So if I run that build, well, that was quick. It's done everything. So you can run it with verbose if you want more output. Obviously, because I've already built it, it's doing incremental build. There's nothing to do. I can give the build a particular target. So CMake will generate a clean target if you want. And then if I build it with verbose, you can actually see the various commands that it's run. So I haven't been particularly clever. I haven't kind of like asked it to use Clang or GCC or anything. So it's just used userbin C++ from my system. And that's probably a relatively old version of GCC. I had a quick look and I thought, yeah, I'm probably due to upgrade this this machine that I'm demoing on from Debian old stable to stable at the very least. But I decided in a fit of being very sensible not to do that in the hours before giving a talk demo. So that's that. Fairly simple, fairly easy. It works the same way if you've got a big complex project. It just takes a lot longer. So if I can find my slides again, pop back to the slides. That didn't seem too bad. So yeah, you get a lot of people complaining about CMake. So one of the things I've learned is that people don't like to spend their time editing CMake files in general. Yeah, that didn't seem too bad. Why does it get so complicated? And the answer is, of course, as soon as you're out of demo land, projects hit reality. Dependencies get complex and involved. You have dependencies inside your projects that the different parts of your project depend on. And then you have dependencies outside of your project, so libraries you depend on. Where are they installed? What are they required to do? What are the complexities? You know, how should I find them? How should I make sure my CMake list is portable so that wherever my dependencies are, my project still builds? And so yeah, the real world and real world complexity tends to mean that things get more complex than they are in demo land. So what we saw in that was an example of creating a target. So very much the same terminology as make. A target is something that CMake wants to generate, and typically it's something like a library or an executable. You can also have custom targets. So add library generates a library. It can generate static libraries or shared libraries. Add executable adds a task. There's probably a few other specific ones, but then there's also add custom target, for which you can provide your own command for generating a target. And those are kind of like the basic building blocks of your CMake lists file. And then the other big kind of structural thing that you might wish to do is to add a subdirectory. And a subdirectory is what it says on the tin. It's I think it's always a subdirectory of the top level task. I'm not sure if you can add subdirectory something outside of the top level CMake lists. Possibly you can. Probably it's a bad idea. Typically you add a subdirectory is a directory on disk that's the level below the one you're at. Sometimes I've seen projects kind of skip a level, so you've got so maybe if you've got some level of organization in folders, that doesn't kind of like map naturally to a particular target. So maybe you have a libraries folder for your top level, and then you have maybe you organize that into various library groups, but they don't kind of make anything. You might add subdirectory group1/library1 and not have like an intermediate CMake lists that does nothing but add subdirectories on its level. Both of those are valid options. My advice is to kind of keep it consistent. So choose a consistent structure. Name your targets after their output. It's possible to kind of like have one convention for your target names and then set a particular property to make sure that they get a specific name on disk. I tend to avoid that. Oh, and the other thing I'd say is like, yeah, keep your subdirectories portable. So one thing that it's possible to do is it's possible to call add subdirectory and have the CMake lists in that subdirectory structured as though they were a top level project. So they would have a CMake minimum required directive, and then also it's a command technically, CMake minimum required command, and also a project command. And what's kind of useful about that is you could have a library, you could split out into its own build if you're going to make it a dependency that's part of, say, multiple projects, or you could kind of build it in isolation on its own. So, I mean, there are a whole lot of strategies, and interesting, they kind of like, they dovetail in some ways to how you might structure a repository. And if you keep your subdirectories what I call kind of portable, so you can kind of build them separately, but also kind of include them somewhere else, you're not restricting your project structure choice by the way you're structuring your build system. It gives you kind of maximum flexibility. So yeah, I advise kind of like keeping it so your subdirectories are happy to build on their own, and also build as part of a higher level project if they get included into that higher level project. It can be useful. Yes, so what I've demonstrated there was an out of source build. So old-fashioned Unix projects that you might download and do /configure make install. Typically, if you just do that sequence of commands, they build object files into the source tree, and you have stuff that's muddled together, both stuff that was in the tarball you just unpacked and stuff that your build system generated. And that's messy in some ways. It also has downsides. You can't kind of like make a debug build and a release build at the same time. CMake strongly encourages out-of-source builds. Apparently, it is possible to do in-tree builds. Avoid that. And also, in any custom commands that you create, avoid during either at during the configure step or during the build step, avoid creating or modifying files that are in the source tree. There's multiple reasons for this. It means if you do modify files in the source tree during either configure or build, it means that you can't run two different builds simultaneously from the same source tree. So you couldn't build a debug and a release build at the same time. They might both try and modify the same file, possibly in a different way. Maybe it will only cause a race condition because they're trying to make the same update. Avoid creating files in your source tree. That has other advantages. It means you're not going to, so in combination with your source control tool, you're not going to accidentally add generated files into your source tree. So it's especially true if you're doing code generation. If you're creating extra source files, then they're probably not going to match an ignore rule by default. So it can be quite easy to add source files in, and it can be really tempting to, like, I want to create a header file and I want to stick it in this source directory because we already have this on the include path. I recommend against that. Just add the include path to the build area where you're generating the file. It tends to be the more sensible approach. So I see there's a tip, use a CMake presets.json. I have slightly mixed feelings about CMake presets.json. I think they're a really great idea. It's slightly, I can understand the decision. It's slightly sad that you actually have to specify, and I believe this is still true, it may not be, do tell me if I'm wrong. You have to specify, I want to use a preset, so you have to do CMake -, preset, my default preset, or whatever it is. Otherwise it doesn't use it at all. But yes, if you do find yourself wanting to specify CMake build type debug and turn my build option on and use generator ninja, much easier to create a preset that does that and then just call CMake my preset than it is to kind of like verbose write out longhand those three things that you always like to override. So yeah, out of source builds. If you want to make sure you've got kind of a clean out of source build and you don't modify anything in the tree, yeah, you can mount your source tree read only. So I do quite a lot of my work in Docker, and one of the things that I set up, which for a number of reasons, was having a volume that is where I check out my source to, and a separate Docker volume, which is where I configure my build output. And one of the things that I kind of realized after doing that for a while is I can actually kind of start a container for running builds separate from the container that I use for editing stuff. I can start a container for running builds where the source tree is actually mounted read-only, and the build system only has access to the build directory. And so if you're kind of like, if you're going to take my piece of advice that says, don't generate stuff in the source tree, generated in the build tree. If you're going to take my advice and you're trying to clean that out, you want to say, have I got everything? Have I made it so that everything is generated in the build tree? One way to ensure that is to mount your source tree read-only and check that you can build from there. That's quite fun. Okay, so we've talked about creating targets. Quick time check. So one of the most common things that you need to do in a build system is specify the dependencies between various of your targets. And the most common way to do that in CMake is with target link libraries, which sounds like a command that's going to make sure that your target is linked against certain libraries. But in many ways, and it is, but in many ways, the command is more flexible than that. It is specifying a dependency is a kind of more general kind of way of describing it. If you've got custom commands, so there's a quick question coming in. So just to be clear, are you suggesting? I actually got these questions much better than I thought I was going to, so I can see them as they come in now. It's really good. So am I suggesting to place generated source files in the build directory? Yes, I am. I'm suggesting that is the best way forward. It has slight disadvantages in that If you don't generate them in configure time, so you haven't, so it has slight disadvantages in that they are a bit hidden away at this point. So if you're trying to find them to edit them or check that they look correct, they're a bit more difficult to find. But generally with most compilers and debug pairs, the debugger will know where to find them. So you'll have, if you're debugging a program and it steps into a generated file, your debugger's going to have no problem picking out the source file and saying, here's the area of a call stack around where you're debugging. And again, that does also kind of point back to if you're using CMake to generate an IDE configuration, again, that's kind of like saying, if you generate at configure time, you do have the advantage of you can tell the IDE where they are. So yes. So target link libraries is about specifying dependencies. The reason why I say it's a bit more general than just ensuring your target links against a library is you can also specify target link libraries for static libraries. So static libraries still quite, still a very common way to set up libraries, especially internal to a project. They don't generally, I have seen people kind of like create a static archive library which contains all of the contents of another archive library, but it's not generally the way people work. So generally, if you have a library that has a dependency on another library, and they're both static libraries, because it uses the functionality of that second library, generally it means is that when you come to linking your executable at the end, you need not only the library that you directly depend on, but also the library that it depends on for various functionality. You need to link both of those into your executable. And so what you can do in CMake is you can say target link libraries on a library and say library A depends on library B. It doesn't actually link library B into library A, but it means that any executable in your project that specifies a dependency on library A, because the dependencies you've told CMake about the dependencies, it will set up a build rule, and it'll show that both library A and library B appear on the final link line. Things are a bit different for shared libraries, and shared libraries that include static libraries. It can work. It can be a world of pain. I tend to recommend either static libraries throughout or shared libraries throughout, because mixing them, yes, tends to require a lot of care, because you can set yourself up for interesting disasters. So add dependencies, it also exists for an explicit adding a dependency of a target onto another target, usually just used with custom targets where they're not some sort of C++ link step, but just something needs to be built before something else. Okay. Demo time, linking. So I was just going to show a couple of aspects of linking in the second project. So I'm going to switch shares again, and I now have confidence that this will probably work. So I have another project here, and I've got 2 source files, 1 header file, and a CMake lists. And if I look at my main function, I'm going to include a header file that defines print hello world, and I'm going to call that function from a library rather than printing hello world myself. And that hello function is supplied by the hellos.cpp. I'm going to have a quick look at my CMake lists. So for now, I'm just going to, I've got the library section right at the bottom of the file commented out for now, and I'm just going to try building my executable and telling it that it depends on the myprint library. So if I rerun my copy of that CMake file, I could have had a CMake user presets.json, but I don't. There's nothing wrong with the build step. That works absolutely fine. And then if I run my build verbosely, I can see that I get a link error. And the link error is I cannot find the myprint library, which is not surprising because I haven't built it. So, but you can see here that CMake has passed to the linker, I think I can highlight that, has passed to the linker a fairly standard library link directive, which is like the -l, link against this library, it's called myprint. And so it'll use standard system search paths to do that. I haven't actually told CMake to use any other search paths, so you don't see any -L directives in my link line. But that has failed because like myprint isn't a standard library. So I'm going to go to my CMake lists, and I am going to comment in the library step. So some things to note here. I've already told CMake that I want to link hello against myprint, and although CMake lists files are interpreted sequentially, and so at this point I haven't told CMake that myprint is a library I build in this project. I've just said I want to link hello against something called myprint. And now later on in the sequence of events, I'm going to tell CMake that I want to create a target which is of library type, and I'm calling it myprint, and it's going to be built from the hello.cpp. And then I'm also going to tell it about some include directories. So I'm going to do something interesting here. I'm going to no longer explicitly tell CMake to use the current directory as an include directory for the hello executable. And now I'm going to rerun the build. Now, because I've touched the CMake lists file, CMake will know to reconfigure first. It's not just going to, okay, it is going to blindly execute Ninja. But one of the rules that it's told Ninja about is if the build rules are not up to date with respect to any of the CMake lists files that I've parsed, I want you to reinvoke me, CMake, before doing the rest of the build. So you'll see that I ran CMake --build, but the first step that Ninja did was to run CMake again with a special regenerate during build option. And then there's CMake output of configuring generated build files written. And then Ninja is kind of like rerun the regenerated build files. And I've actually got a successful build here. So you'll notice there are 3 steps now instead of 2. Was I expecting 4 steps? Was anybody expecting 4 steps? Yes, I think I might have expected 4 steps because the thing that we built originally, we compiled main.cpp. And this time around, we haven't had to compile main.cpp because main hasn't changed, and the rules to generate main.cpp.o also haven't changed. So it's up to date already. There are only 3 things to build. So it's compiled hello, which is our library source file. It's then, I don't like to use the word linked, although CMake does use it. It's then created the archive library from the source files. So it's created libmyprint.a from the hello.cpp.o. And then finally, it's linked my executable against the library. So there's a couple of things to note. One is like I didn't say that the current directory, the current source directory, was in the include path of my executable, but I did tell my library that the current path should be in the include directory of the library. And I'm going to go back to CMake lists again. So target include directories, I said use the current directory as an include directory for my print library, but I also said use the keyword public. And what that does is it says not only should this include directory be used when building this library, it should also be used when building things which depend on that library. So whereas before I said, hey, this executable uses the header file in this directory, I haven't bothered to say that because really the header file in this directory is part of the library. I've just told it's a library include, and that's propagated by executable automatically. And the other thing that I just wanted to note here is when CMake finished parsing all of my input files, it noted that my print is something that it generates. So whereas before, when I had the link error, it didn't have my print as a target. So it just assumed it was some sort of a system library, and so it used a -L directive. Now, it knows that it's generating my print. It knows it's generating it as a static library, and it knows where it lives in the build tree, which is actually in the current build directory, because I've got a single CMake lists and everything is living in the same folder at the moment. But what it's actually passed through here, so if this is part of a subdirectory, it might have myprint/libmyprint.a. What it's passed here is like a relative path in the build directory to where it knows we're actually generating it. So if you create, and this is kind of like something that might surprise one, I suppose. I'll just go that far. But what it does is it does mean that if you specify that my print is something that you build, you're not if something's gone wrong in your build directory, say you didn't add the library to the all target and you didn't set up a dependency correctly, or something, or you've changed the name or something, you're not going to accidentally pick up a system library when it's something that CMake believes that you're trying to generate yourself. So that's kind of like, yeah, just something to be aware of. I don't think it's kind of like, I was surprised. I don't think it's ever kind of been a gotcha for me, but it was definitely a surprise when I kind of learned it did different spellings based on whether it's something it generates or something that it doesn't generate. But yes, if you think that your CMake file should be trying to generate a library, and you notice that when you're trying to link it, it's using a -L directive, that's probably because CMake doesn't think it's trying to, it doesn't agree with you. It doesn't think it's trying to generate the myprint library. Cool. Right, switch back to slides now. So button. There we go. No, not. That's the one. Right, there we are. Okay, so the next part of this, and I'm going to have to move faster. So logic and state. So we've talked about how to do kind of basic things in CMake. And now when you're kind of like extending it, you're probably going to want to do some logic. So CMake has 3 flavors of variable, all of which have their own properties. One of which you're probably already familiar with, even if you haven't dabbled in CMake, and 2 of which you won't have come across. So regular variables. So regular variables you just set with the set directive, and then they tend to be expanded in a shell style syntax with these $curly brace. And so you can have spaces in variables. They can contain pretty much anything you want, and then you can expand them in pretty much any CMake command. I've chosen the message command here. Message command is fantastically useful. In CMake, you can end up doing some like printf style debugging, and like message is the tool for that. You can do message debug, and then it'll only appear if you specify log level equals debug when you invoke CMake. But status messages are printed by default. So if you use them sparingly in your extensions, they can be quite just useful to state what you're doing, what you've interpreted. They have dynamic scopes. I'll talk about scopes a bit later on. They're not preserved from CMake run to run. So if you run CMake to create a brand new build directory, and you run CMake again to reconfigure with any change settings, when you come across a set or when you come across the use of that variable won't be set if it was set in a previous run. Everything starts with a blank slate on a new invocation of CMake. Cache variables. So cache variables have a global scope, So if a subdirectory sets a cache variable, a parent directory or a module that you include that's included subsequent to that can read the same cache variable. They are preserved from run to run, and they're stored in the CMake cache.txt. So we saw that in on disk in my first demo. I kind of alluded to the fact that it exists and then declined to go into any details about it. This is what it's here for. It's here for cache variables. And then finally, we have environment variables, which are just regular environment variables. They're inherited from the calling environment, which is exactly like any other process on most operating systems where CMake runs. Environment variables, they're not preserved from run to run, but if you run CMake and you run CMake again, it's liable to start with the same environments. So, but if inside your CMake list you specifically set an environment variable, that setting will be lost when CMake exits. Environment variables are propagated to children, never the reverse, and that's just a standard kind of process propagation. However, an environment variable might affect something that gets written out into a cache variable. So one canonical example is like in a very similar way to the way a typical configure script runs, you can often run with some well-known popular variables like cc equals /user bin my custom C compiler. Configure will say, we want to set this to be the compiler you want to use. CMake has exactly the same mechanism. If you run CMake, there are a set of variables like C flags, CXX flags, CXX that can affect your standard global flags and compiler path that you want to use. However, the way that CMake does is it reads the environment for some of these variables, and if it finds them, it tends to write out a cache variable with the contents of that variable, so that in your CMake cache you can see which compiler was selected and what C flags. If you run CMake to reconfigure the same build directory, it's the settings in that cache that gets used for most of these variables. And this can cause surprise. So if you incorrectly set an environment variable that affects how CMake initializes the cache, and then you get an error, you think, oh yeah, typo, and then you run it CMake again with a different environment, you may find that the setting that's written into the cache takes precedent. And even though like running the same command with the fixed environment variable should be the right thing to do, you've lost that chance. You've written into the cache something that doesn't work. And the solution to that is, well, typically I find that's happened so early in the process that I tend to just delete the entire build directory. But you can also selectively update the cache and then delete the CMake files directories. But generally, I'd recommend blasting away your build directory and starting again, because typically this just happens on the very first configure anyway, so you're not kind of losing a lot. And the other thing to note is like the environment variable that's set at the time that you configure, that doesn't affect the build process at all. However, you may be running your build process in the same launch environment. But again, if you set an environment variable in CMake lists, that's not the environment in which the build is invoked. So yeah, it's kind of like normal environment variable gotchas, but just like here again in the CMake world. Yes, so yeah, watch for caching bad values. That's phenomenally easy to do, and it's kind of like, especially if you're not quite sure, if you're using some module and it says, set this to this or something, you try a few things out. It's very easy to kind of like try something that doesn't work, try something else that gets a different error, switch back again, and then after some lost hours, you realize it actually was something else cached the original thing that was bad and it was never going to work. Yes, this has been responsible for a non-zero number of tweets I've made about CMake in my life. Yeah, set doesn't always set. So another thing, if you call set for a cache variable, and that cache variable has already been set either in a previous run or by a module you've included or specified on the command line, that set action may not actually set the variable. So you can override that by using the force when setting a cache variable. There's a force keyword. Generally not a good idea, but again, it's kind of something to be aware of. Yeah, and I tend to recommend against environment variables unless you kind of really have to for a specific purpose. Types. So what types do variables have? They're all strings. This is easy. That's it. However, we can treat strings as lists in some contexts, and we can also treat strings as Boolean values in other contexts. So I'll come on to that a bit later. Yes. Lists. Lists are a bit messy in CMake. They're just strings again, and therefore the implementation and detail of lists leaks through really easily. So what a list, how a list is implemented in CMake List is just semicolon joined list of strings in a big string. Lists split into their component parts when you use them in commands sometimes, and they're split on semicolons. And in that context, they are split in semicolons that are not prefixed by a backslash, and backslash prefix semicolons are translated into semicolons. When you put a list, when you go the other way, so you kind of like create a list or you append a list to another list, yeah, you can kind of like through variable expansion, you can do $brace expansion and then tack on a semicolon and then some other component. And things that do that tend not to escape the semicolon. So it's advisable to like just avoid any situation where you might want to put something with a semicolon in a list. It's fragile. It's going to break. Yeah, avoid it where at all possible. And if you were trying to use the list abstraction, this is where the fact that it's like semicolon joined strings just becomes all too obvious all too quickly. But CMake has lots of useful inbuilt ways of manipulating strings in the list command. Yeah, look it up. The documentation's pretty good. You can append things, do something to each member of the list, transform them. You can iterate through lists. Yeah, all good stuff. Oh yes, so I've talked about the gotcha of lists. Yeah, so when you're evaluating a string or a variable that is stringy in a Boolean context, CMake makes, I don't know, is it unfair to say CMake makes JavaScript look logical? There are a number of falsy values for strings that can be quite surprising if you didn't know about them. So in particular, if a string ends in dash not found, it's considered to be false. And the reason for this is CMake has a number of inbuilt commands such as find program, which looks for a program on disk that might be executed as part of your configure step. And if it doesn't find the program, it sets the variable to the value of the name of the variable dash not found. And the reason it does that is the variable will start out unset. You call find program, it will search through your disk, and it wants to make a distinction between I haven't looked for this variable yet and I have looked for this variable and not found it. So it doesn't use undefined or the empty string for I haven't looked for it yet. It uses dash not found. And that saves the next thing that looks for the same program from doing the search path if CMake has already determined that it cannot find that program. But yeah, out of context, you probably wouldn't expect XYZ dash not found to evaluate to false or off or 0 or other Boolean negatives. So cache variables have types, or at least they're given kind of like type descriptors, which can be quite useful in knowing how they're used. In particular, one thing to note is if you pass so when you you may have kind of come across passing variables on the command line. So similar to many preprocessors and compilers, you can do a -D flag in order to set the value of a variable when you invoke a program. CMake again uses the -D to define a variable that you pass in on the command line. -D in CMake is always setting the value of a cache variable. So anything you pass in with -D is specified as a cache variable. If you pass in the value of something that's a path or a file path, it gets absolutized for you automatically, which again can be a surprise. Check my one notification. Okay, I haven't seen the yeah. Yeah, okay. So I did say earlier on that set doesn't always set a variable if a value has already been given. There is something kind of interesting though. It's if you do pass in a -D, a cache variable with -D on the command line, if you have a set command that corresponds to that variable name, although it's possible to specify a type label on the command line, most people kind of don't. But I think trouble being full screen is I'm not quite sure what comes up next on my slide. So actually this slide is, yeah, really useful. Say I did, say I have this set my cache var in the in my CMake lists where I give my cache var the value of cached value. If I use -D to like override the initial setting, then other things like the type, so the string, and the documentation string, so important build settings, get attached to that that variable that got passed in. So while set doesn't have the effect of actually setting the value of the variable, the other labels which end up in the CMake cache file do have some effect. And the other thing I wanted to note is that Boolean cache variables have got a synonym, which is an option. So often, they're usually used as build options. So if you use the word option, it implies cache bool and a default value of off. So option, build option, enable picky insertions is the equivalent of doing set my build option off cache and then the documentation string. So yeah, I think that's added just because build options are kind of quite a common feature, and yes, having specifying the rest of it it can be a little verbose. Cool. So once you've set a variable, as I specified, you can kind of expand it in various ways. There's a way to disable expansion. You can use bracketed arguments. So that's a way of specifying a literal argument into a CMake command without having any variable expansion done. If you put a variable reference into double quotes, that gets expanded into a single word. And if you put a variable expansion not in double quotes in a command invocation, that gets treated as a list if it contains any semicolons and split into multiple words. So if you know that a command takes multiple words and they may be kind of like keywords and options, you can use a non-double quoted variable expansion if that variable contains a list of valid options for that command. And, if. So if is magic and special and will automatically do variable expansion even if you're not using the $curly brace instance. So this makes for kind of this is so commonly used that I have no issue using this kind of unquoted one. So if var name says, if var name exists and expands to something truey, then it is true, and if it doesn't, then it's false. However, it kind of got, and this is, I think there's a behavior change in the middle here. So I think there's a policy change. So if you're using an older version of CMake and you haven't, or a newer version, you haven't specified a minimum version required that spans that policy change. If unquoted $var name would replace var name with whatever the var name contents were, and if that happened to name a variable, it would expand it again and then evaluate whether the name of the thing that it referred to looked truey or whether it looked falsy or not. And I just think that's, so even if they hadn't changed the behavior, I just think that's too surprising. So I kind of stick with either if bare word or use a double quoted explicitly expanded variable, because like a double expansion of something with dollar braces is too surprising for me. The other thing you can do is you can directly reference cache variables. You can also do with this environment variables. So you can say look for this thing and it must be a cache variable, and then you can kind of test on that. I tend to avoid that. It tends to be a reasonable practice to allow CMake lists to kind of like specify something to override and hide a cache variable specifically. I can imagine there are probably specialist circumstances where you might want to do this, but I haven't really come across many. I've thought about doing this on occasion, but yeah, no. I am starting to run out of time, so I'll go reasonably fast. So running custom commands. This is typically where people need to keep a clear head about what's configure time and what's build time. There's a command execute process, which runs either a single command or a pipeline of commands, and that happens at configure time. And so the output of that command in some form, sometimes a variable, is available at configure time, and you can take action based on the output or the result of what it's done. You can look at what it's generated on disk if it's that sort of command. And then you can also specify custom commands to the add custom target and add custom command commands. And these set up build rules to be run at build time. So when you say add custom target, grep this stuff on disk, that will be executed. That will not be executed during the configure step, but a rule will be set up so that thing will be run at build time, possibly in parallel with other stuff from the build directory. And so that has like advantages and disadvantages. And it's just kind of good to keep clear in your mind when you're expecting things to run and what sort of environment they're expecting to run in. I've just explained that slide. Okay, cool. So last topic, kind of building a module. There are kind of like 3 ways to build a module. The simplest one is to just create a CMake file and then include it. Then there are 2 others which are, I guess, intended for perhaps separately distributed modules, things that are not. You probably want to use include. You probably end up using include if it's like part of a particular project, and you're just kind of extracting out some CMake logic into a separate file. If you're going to kind of create something that you're going to share between different projects, make it kind of like reusable, you might use a module or a config module. There's actually no great difference between these. Generally, the second one, defined my custom CMake, it's generally used, supplied by people writing CMake for something that already exists that doesn't have knowledge of CMake. So I mean, they're already it's already like a find library function, but I just by way of kind of illustration, say I think find curses is a built-in module that's a bit like this. So say you want to just like link against the curses library, and sometimes that's ncurses, sometimes it's raw curses, sometimes you need to specify libtinfo as a separate library as a dependency. So the type of module that uses find is typically kind of like a CMake module written to find something external to CMake and to kind of like just make it easy to use something that may be found in a kind of number of different configurations. And then the config module tends to be the one that I can tend to opt for. The differences are really in the way that the modules are found and loaded, but how they actually kind of operate in practice is very similar. So variable scope, when you're writing a module, you tend to kind of like come up hard against CMake's rules for scopes. So when you set a variable, it's visible for the rest of that CMake's lists file, but also is visible in subdirectories. So what happens is when you enter a scope, and there are two ways of looking at it, and I think it differs. I think maybe technically internally it differs from when you call a function when you go into a subdirectory, but I'm not quite sure of the internals. But the effect is when you enter a scope that's a subdirectory, or when you call a function, variables set from the enclosing directory or the calling environment are either copied down or visible, depending on which way you look at it, from the parent scope. However, when you modify those variables, what you're modifying is a copy that kind of shadows the parent one. And then when you exit a subdirectory or leave a function, that variable that copy disappears, and what's visible in the enclosing scope is what the original value was. And this is sometimes helpful and sometimes very surprising. So new scopes are created by subdirectories or functions. So when you change a normal variable in a subdirectory or function, that does not affect the copy in the enclosing scope. There's no new scope created by including a module or by calling a macro. And I think this is quite surprising. So why it might be useful is you might invoke a module in order to set some variables. So being able to do that is kind of useful. But if that module defines a function and calls a function, then the things set inside that function will not be visible after that function call, whether that function call happened directly in the module or that function call was called by something that included the module and then called the function that was provided by that module. And scopes are also not created by macros. So this is like about the only difference between a macro and a function. And that means if you want to kind of like directly manipulate the calling environment, then a macro is probably what you want. 10 minutes left, is that right? Yes. Okay, cool. Yes. So regular variables get their initial value from the parent or calling scope. What's quite interesting is you can unset a variable, and even if that variable came from a parent scope, so if you unset it in a subdirectory, that means that variable will look unset, even though if you return from that subdirectory, there may be a parent variable with the same name that suddenly becomes visible. However, if the parent set a variable that shadowed a cache variable, in the subdirectory, if you unset that variable, it might make the cache variable suddenly visible. So if you had a variable expansion after an unset, it might now expand to the cache variable. And that can be surprising. Hopefully it's quite a corner case that people don't come across a lot, but yeah, that can definitely be surprising. And I think I've kind of like, yeah, so changes to non-cache variables are kind of lost when you get back to the calling scope. So the only exception to this is some set. So the set function and some things which are a bit like a set function sometimes have a parent scope option that you can call, where you can deliberately say, hey, I want to set this variable in the parent scope. And they can kind of hop up one step at a time. But yeah, you can't kind of like set something at the top level in a function that called a function, or in a subdirectory that added a subdirectory. There would have to be cooperation to pass it up one level at a time. So yeah, my recommendation is to avoid having to do that or trying to do that. Probably the most sensible thing is to consider a cache variable if something is needed that globally. Yeah, so there's no file or module scope. When you do something like find package module, and that the source for that module starts getting interpreted, the sets at the top level in that module are affecting the thing that included that module. I think I find this the most surprising thing. And it also means another thing is like there's no, you can't have like file statics in a CMake module. You can't say set this variable and then have functions able to kind of interact with that variable whenever those functions are called after that module has finished being interpreted, and when functions from that module are going to be called. It's something that I've kind of felt I've wanted to do, and then found other ways around when I discovered that this is not the way. Possibly a well-named cache variable that's got the appropriate scope. Again, that has advantages and disadvantages. It's like when you reconfigure, if you've set a cache variable, obviously that will have, the second time around, that will have a value right from the start of the execution of the configuration step. Writing a function using the function command, stick to lowercase and minimize the number of required positional arguments, which is what named arg is in this case. Stick to lowercase because you can use any case when calling a function, but yeah, generally that's a little confusing. So yeah, limit the number of required positional parameters. CMake parse arguments is a helpful command that lets you parse arguments in a way that's fairly that gives you kind of like native CMake style commands. And the other thing when writing a function is always unconditionally set your local variables. So if you have some sort of maybe you have a list of outputs maybe that you're adding to some target in some custom CMake thing, and you just like use list append to append a whole lot of things, and then you do something with that list at the end. It's very easy to not notice that list, the variable that you're using as a list name, you never set it to blank right at the top of your function. And so maybe you're operating on something of the same name that got copied in from the parent scope. This one has definitely affected me before. So I always make sure to explicitly set a variable that I believe to be local to my function, just in case it proves not to be local to my function. So I had a very quick demo just to show an example of what you might do. And yeah, pile up questions. I don't know how long I'm allowed to overrun, but let me just switch share and show you this module. So I created an example module which I called library info. And the point of this module is to add a function to a library that has got a standard name and gives you information about the library. And what I decided to do is to call the function target library info, and it takes a single required argument, which is a target. And this kind of this naming and parameter passing kind of is reminiscent of the way inbuilt CMake commands like target link libraries are named and operate. Perhaps it's a bit too generic. Maybe I should have given it something. I mean, all of the words target library and info are fairly general words, so I probably have a high possibility of clash with somebody else doing the same sort of thing. So the first thing I do is I call CMake parse arguments to parse all of the optional arguments. You can look up the documentation. This basically takes a special variable prefix. I'm using the parseargv flavor that just says parse the arguments to this function, and not some arguments that I'm going to pass explicitly. And then I have a number of options, a number of single argument parameters, and a number of multiple argument parameters. And I'm only using single argument parameters. So for this function, I've decided that you'll be able to pass a description and so optionally pass a description, optionally pass a prefix, and optionally pass a namespace. Actually, in here, the description I feel is not optional, and I could put a check in here. So in fact, I probably should put some error checking in here. I haven't done, bad me. But what I can do is I can. So what CMake parse arguments does is it parses the arguments and then sets variables which are. Sorry, I keep flashing the screen because I hit the wrong key. And then sets variables with this prefix based on what it found in the arguments list. So if you supply a prefix, it will set TLI args prefix to that value. And what I've done is I've said, okay, if you supply a prefix, I'm going to use the prefix you supplied, and otherwise I'm going to just use the name of the target with an underscore. Then I'm going to kind of show off a bit of string magic. So string is a built-in function that CMake provides for manipulating strings, and I'm just going to uppercase prefix and store that in the variable prefix all uppercase. Again, I'm going to optionally parse a namespace, and then I'm going to set description to description. Now, this is probably where I should have checked whether you actually supplied a description and errored if you didn't. But hey, that's another name. It would expand to blank if you hadn't. I'm using another useful feature of CMake. I'm using the configure file command. Configure file essentially copies a file from somewhere to somewhere else, optionally replacing keywords in it. I think probably this is just a variation on the most common use case. It's very much like a config.h.in that old-fashioned configure scripts would do. And so I've got some template files for a library info, which I'm going to copy into the build area, and I'm going to give them a name with the prefix for the library. And then I'm going to add these custom generated sources to the target that has been specified. And then I'm going to add the place where I generated them as include paths for the library. And finally, I decided to use some C++17 features in these templates. So just to be sure that you're building in a C++17 aware world, I said, oh, by the way, if you use this module, your target is going to be requiring C++17. So just have a quick look at the template file. I'll just look at the CPP one for an example. So I include the header file with the right prefix. In an anonymous namespace, I put the description that got passed in. And then the function I supply is called getLibraryInfo. It's in your library's namespace, and it just returns a string view of the description. And I'm sure people will be delighted to tell me better ways to do this in C++ 23 or something. The -1 slightly bothers me in the size of, but hey. And then if you look at the CMake lists that I have for actually building my library, so this is a variation on the second example. I'm using find package to include my module. Now, the simplest version of this will be just find package library info required, close brackets, and that says find this package and just error out if you're unable to find it. If I left out required, it would like try to find the package, and then if the package wasn't found, it wouldn't worry about it. But because I haven't installed my module, I'm just using it from the current directory. I said, oh, here's a hint, just look for it in the current directory and don't bother to look for it in any standard places. And then I'm adding my library with no source files itself. I could have added another source file for demo. And then I'm using my function that's been provided by the library to add this, this useful description for my library. And then hello this time, rather than print hello world, I've decided to just print library information. So if I just run my favorite configure, that builds fine. And then if I run, and during the configure step, I will have created these files, these source files from the template. I wasn't very verbose about that in my module. I didn't make any kind of status output. And then if I build it, see there are 5 steps here. Again, I'm just going quite fast because I'm kind of out of time. And then if I run hello, it's created my it's printed out my library description string of useful library v0.1 for things. So yeah, you can see how this might be useful if you like to stamp a version all throughout all of your libraries in a big project. Just making that a kind of a one-liner can be kind of quite useful. Cool. Yeah, questions, bearing in mind I'm not an expert. Do you feel there are any particular features or reasons why CMake is often preferred over similar tools? I don't have a good answer for that because I haven't used many other tools. But hey, perhaps that's a tool. Maybe there aren't that many tools out there that do what CMake does. I think CMake has is reasonably flexible, and in the simplest case, it's fairly easy and regular to write CMake lists.txt. There are like a lot of quirks in the language, but not so many that put you off if you kind of like follow best practices. Yeah, I don't have a kind of great answer for that, but it definitely has won enough market share. And I think with build tools, there's a temptation to make them. So I think there's a tension in I mean, a build system will tend to introduce a type of domain-specific language, and I think there's a temptation. There's a tension between simple and regular and predictable against fully flexible. If you have a build system that is too flexible, you can't predict what it's going to do for any particular project, you end up having to spend more time and energy maintaining that structure. If it's kind of more regular and you keep it simple, you don't have to spend so much time in there. So I think CMake's, I think the negative of having some quirks and inflexibilities is not a particular disadvantage if you're using it in the best possible way, or in a way that's doesn't require your developers to spend too much time editing CMake files, which I think is probably a good aim. Okay, that's answered everything that was kind of popped up. I hope you found that interesting. It's been fun. I need to have some water now that my throat is completely dried out. And yeah, enjoy the rest of the conference. I shall be often online in the Discord world for a while.